Okay, I can't believe it's showtime already, but thank you to my hosts, and thank you for attending, and welcome to my listening room. And let's have some fun today. I've got some weird amplifiers for you and some other things. And don't worry, everything you see today, there will be more details posted online at a later time. So if you need bills of material or parts lists, or you have questions, you can ask those in the Q&A. So let's light this candle. Okay, so here we go. I guess the advantage to doing it this way is I get to do this in my pajamas. So let's kick it off with the Mofo. This is a follow-up to Mofo, and I think I posted a simplified schematic for this online back in, what was it, 2017? I've been out of the picture for a while. So at any rate, I finished it up, and let's take a look at it. So it looks a lot like a regular Mu follower, except that in this case we're driving a P channel MOSFET there, Q2, and it's operating such that the output comes from its source. So this is a follower, and the benefit to doing things this way is that we get a little bit of push-pull action from this depletion mode transistor on the top, and the current is set by Q1, and those two resistors, R5 and R6, and those are selected so that we get somewhere between 1.4 and 1.5 amps. And these transistors are still around, and however, selection can be a little tricky if you don't have a lot of them. So I've taken care of that for you, and this will be a parts kit offering at some point, and you'll get selected transistors with matching resistors to get you where you need to be. The little divider that's made up of R4, P1, and R3 is there to set the midpoint at about 18 volts. This uses a 36 volt switching power supply, similar to the one, or the very same one, as in Nelson's VFET follower. So I thought we'd just reuse that one here. Here's the THD for 8 ohms, and you can see we're at about 0.06% rather at a watt, and we're getting out to maybe 12 or 13 watts before we hit 1%. And I don't know, maybe between friends we can call this a 15 watt amplifier. Now remember that we're idling at 1.4 amps, and yet we're able to get about 2 amps peak out of this, and so that's that little bit of push-pull action that we're getting from the Mu follower. And then here's the THD into 4 ohms, and distortion's a little bit higher, and we get a little less power out of it. But in case you intend to use it with a 4 ohm speaker, there you go. And now here we have the THD versus frequency. And you'll notice it's pretty flat, and then we get to about 2 kilohertz, and we see this rise here. And if I'm not mistaken, and we can double check with Nelson on this. That kind of looks like the IRF P-channel shelf, and if that's the case, maybe we can convince Nelson to part with some of his Harris P-channels and see if we can improve on that. Here's the frequency response, and you can see it's pretty flat, and we're down about 2 dB at 200 kilohertz. And here's the 20 kilohertz square wave, nice and clean. And this is the distortion residual. This is the fundamental, and this is the distortion residual here. And you can see that's I would call that a positive phase, second harmonic. It's off a little bit, and we'll talk about that in just a little bit. Other specs for this is the weighted noise is 6 microvolts without any filtration, and if we use Nelson's filter from the P-channel VFET project, that we can reduce that all the way down to about 1.2 microvolts, which is, for all intents and purposes, that's nothing. Even unweighted, it's 3 microvolts with the filter. The output impedance is 0.66 ohms, which not coincidentally is equal to one of those source resistors. And that makes the damping factor 12. And the input impedance in this case is about 165 k ohms. And the gain is a little less than 1, 0.76 dB. So around the time I published the first Mofo project, I wanted to do a front end for that, and this started out. This started out as a front end for Mofo, and it could be used as such, and we'll talk about that later on down the road. But in this case, I'm using it as a front end for the Mofo. So let's take a look. There are, since Nelson published his VFET follower project, there have been a lot of really nifty front ends published for that, and I think just about any of those would also work here. But me, I wanted to do something really simple and dumb to match the simplicity of the Mofo. And also, in the case of the Mofo, which used a choke as the load, I needed something that would allow us to get enough swing to drive that, because the Mofo has that, it has that quality where we can swing almost twice the supply voltage. So this is, as you can see, this is a choke-loaded JFET in common source, and in this case it's the LSK170A, or it could just as well be a 2SK170 if you have those, which would be the GR variety, or it could be the 2SK370. I think I got that right, and that would also be the GR. And that allows us to use up some of those lower IDSS parts, but also it's the right part in this case, because I wanted to keep the drain current low, because we're going to drop some voltage across that inductor, which has a DCR of about 1K. And you'll notice that this is a 15 Henry inductor, and it's nothing fancy. It's just it's a part that I believe is made by Triad, maybe a C1X, really cheap. It would be nice to have some more inductance here, but as you can see, I've included a feedback network, and we're going to get a little help from that, as we'll see in a minute, R2 and R3 form a negative voltage feedback loop. And if you look at R5, I have that set to 2K right now, and between that and L1, that's putting the drain of that JFET at about 18 volts in this case. We can lower that to 1K and run the drain higher at about 24 volts. If we do that, here's the total harmonic distortion, but rather than show you the output in volts, I've put the output in equivalent watts, because presumably you'll be using this circuit to drive a follower of some sort. And so this is the kind of output power that you could expect. And you can see that it's making it all the way to about 30 watts there with the 24 volt drain. And pretty good distortion figure there. Now if we increase that resistor to 2K and lower the drain voltage back to about 18 volts, you'll notice that the distortion is higher and we get less power. But I'll show you why that's convenient, and we don't need 30 watts of swing for this project. So let's take a look. This is what it looks like with the drain at 24 volts, and you can see that distortion residual is you got a fair bit of third pushing up through there. It's low. It's the lowest figure. But when we change that drain voltage, we move the Q point, and we get a nice negative phase second harmonic, and you can see that's nice and clean. Here's the THD versus frequency, and we're getting a little bit of a, you can see, getting a little bit of a smiley face effect there. That's a lot of that is thanks to the inductor. And here's the frequency response. We're down 4 dB at 200K, so pretty good. Here's the 10 kilohertz square wave, nice and clean. And our noise weighted, and this is with filtration, by the way, is 15 microvolts, and unweighted is 25 microvolts. The output impedance is about 300 ohms with the feedback set the way I have it, and the input impedance is about 10K ohms. Actually, it's a little bit less than that. And you may wonder about that. That may be kind of low depending on your preamp, but most preamps aren't going to have any trouble with that. And if you're driving this with a something like a B1 or maybe an ACP Plus or something like that, you're going to do just fine. You could possibly scale those feedback resistors maybe as much as twice, but at some point you're going to cut into your frequency response. So, and the gain is 19.5 dB, so good amount of gain. Okay, so let's take a look at what this looks like when we put the front end together with the output follower. And you can see here something that's interesting is the blue line, which is with the lower distortion figure here, is actually the higher distortion with the clean negative phase second harmonic, and the orange line is that lower THD figure with the drain at 24 volts. And this is just a good illustration of what happens when you take an amplifier that squishes positive half of the cycle and drive another amplifier that squishes the negative half of the cycle, or vice versa, and you get some cancellation. The two tend to cancel each other somewhat. So we're seeing the benefit of some cancellation here, and all we did was just change the cue point a little bit. This is what the distortion residual looks like, and you can see maybe we can call that a negative phase second harmonic, but it's really somewhere in between, and we'll talk about that momentarily also. Here's the THD versus frequency for the FV1 and the Mofo together. And the smiley face is still there. And guess what? In addition to the smiley face, we've now added or introduced that IRFP channel shelf into this. And that's why we're getting that situation over there. So again, we'll see if Nelson will part with some of his Harris parts. Here's your frequency response. Pretty flat. Again, minus 4 dB at about 200 kilohertz, and a nice happy 20 kilohertz square wave. Some other specs on this. The noise without any filtration is just 20 microvolts. That's weighted, and unweighted is 44 microvolts. If we put Nelson's filter into place, we get that down to about 19 microvolts unweighted, which is, again, I mean, that's just really great. The gain is 19 dB. The input impedance is 10 k ohms, or a little bit less, and the output impedance, not surprisingly, is still 0.66 ohms. And here's a prototype channel, and this will be offered as a parts kit and PC boards in the not too distant future. And a point of note here, you can see I use these little screw terminals in my prototypes, and I recommend that when you build your finished amp that you don't use those, because ZenMod will make fun of you. And also, they can be problematic because, you know, if you screw and unscrew those enough times, you know, you're going to start cracking the traces on your PCB and stuff like that. So, but I use them for prototypes because it just saves me a lot of work, and it's very convenient for testing things. So, yeah, look for that one on the DIY audio store soon. You can see it fits the 4U chassis. And I had a few of these on hand, and so I just made a little plate for the power switch and the power input. I'm hoping that Jason will offer that really cool slim deluxe 4U case that they used for the VFET amplifier. And if that were the case, then that would be a lot slicker here, because right now it just has a big empty space inside. Well, we've been talking about second harmonic and positive phase and negative phase, so I thought it might be good to take a minute to talk about that. Here's a slide. Figure A shows a 1 kilohertz fundamental along with a very large negative phase second harmonic. So you can easily see the relationship between the two on the time axis. The second harmonic is a positive cosine going negative when the fundamental is going positive. And in this example, the harmonic is opposing in the first half of the wave cycle and aiding in the second, which squishes the positive half of the cycle. The figure to the right is a sign with the 10% negative harmonic distortion. Figure B shows the same 1 kilohertz fundamental along with a large positive phase second harmonic. And here the second harmonic is a negative cosine, going positive when the fundamental is going positive. In this example, the harmonic is aiding in the first half of the wave cycle, and opposing in the second, which squishes the negative half of the cycle. So the takeaway is positive squish, negative phase, negative squish, positive phase. So we understand this is distortion, but what's causing all the squishing? Well, it's a well-kept secret in audio that inside every FET is a tiny robot. The currents and voltages here are positive, so this is an N-channel robot. And his job is to look at the voltage between his gate and source and adjust the current flowing from drain to source according to a very simple program. And he should adjust the drain current equal to VGS times GM, which you could think of as the gain. And if he could handle this simple multiplication, he would generate characteristic curves like the ones on the right, and we could have perfect amplifiers. But like all robots, and I'm talking about you, HAL 9000, he has a flaw in his programming. Our robot can't multiply very well, and instead he produces characteristic curves that look like this. Notice how the curves are no longer evenly spaced. Instead, they get further apart as VGS increases. In this example, the robot is working into a load like a resistor or a loudspeaker, which is attached to his drain. And when the gate voltage goes positive, the drain voltage goes negative, and vice versa, inverting the input signal. And because of his flawed program, he squishes the positive half of the output wave. As we saw in the previous slide, positive squish, so negative second harmonic. And this is generally true of N-channel robots, although the characteristics of real FETs are much more flawed than those that we're showing here, allowing for some exceptions depending on the load line and the cue point. We could solve these problems if we could correct our robot's program, but he's locked inside the FET, and we can only talk to him through those 3 pins. One solution is to alter the signal we give him in a way that accounts for his flaws, sending him a signal that is purposely distorted so that he will undo his own errors and leave us with the amplified signal that we want. If we sample the output voltage and mix it back in a way that subtracts the sample from the input, we have negative feedback, and this is voltage feedback. If we sample the output current, that's current feedback. If we mix the voltage back in parallel with the input, we call that voltage shunt. And if we mix the voltage back in series with the input, we call that voltage series. Both types lower the gain, we're subtracting input, and lower the output impedance. Voltage series will raise the input impedance, and a good example of voltage series is the source follower, which has 100% negative voltage feedback and a gain less than 1. Voltage shunt lowers the input impedance, and here we've added a voltage shunt network to our robot. He has no idea what we've done. He just carries on with his program, but now we've modified the signal we're sending him to subtract some of the distortion. Voltage feedback gives us the more triode-like curves shown here. Lower output impedance. The curves are a little more evenly spaced now too, so lower distortion, albeit at the expense of gain. This also provides us with the opportunity to work with the load line and the cue point to either minimize the distortion by load line cancellation or dial in the distortion characteristic that we want. By moving the cue point or rotating the load line around the cue point, it is also possible to find a spot where we flip from squishing the positive part of the output to squishing the negative, and this gives us some control over the phase of that second harmonic, which I'll demonstrate now. First, here's a real-world demonstration of the feedback effect, showing a 2SK170 hooked up to a curve tracer. I'm varying the voltage feedback from 1% to 5% or so, and you can see how the drain resistance and transconductance are reduced. So in this demo, this is the distortion residual and fundamental from the FE1 shown earlier, and that's a fairly clean negative phase second harmonic. And that's handy for cancellation, as we saw earlier. But what if we want this to be positive? Earlier I showed you the effect of changing the cue point on the character of the distortion. Now let's work with the load. Nothing fancy here. I just clipped a 100K pot in parallel with R4 so I could adjust the load presented to my analyzer, which has a 100K ohm input impedance. So let's check it out. I'm just starting to turn the pot, and you can see that the distortion is getting lower, and I'm starting to cancel that second, and this is probably about the distortion minimum here. And if I keep going, you're going to start to see, here comes the flip. There it is. And I can keep going and going. And there we go. And that's a pretty clean positive second there. In this demo, this is the distortion residual and fundamental from the FE1 plus the output follower. And if you look closely, we're somewhere between negative and positive phase here. And maybe that's what we want. But what if we want a nice clean positive second, so that when we flip the speaker terminal to preserve absolute polarity, we'll be back to a nice clean negative second harmonic. Just like the previous demo, I'm adjusting the 100K pot clipped into the FE1 to find the right match between the front end and the output. So here goes. Starting to adjust, and now you can see that's starting to line up pretty nicely, and there we go. That's a pretty clean positive second harmonic. And I'm going to show you a little trick here. If you can get both of those on your screen like this, you can put your scope into XY mode, and you'll see you've got this little arrow, and that arrow, there's actually a couple loops there, but they're pretty close together, and that means that we're lined up pretty well. If those loops were more visible, that would mean that maybe we're not lined up so well, but in any case, you've got this sort of arrowhead shape that points to the left, and that's a positive phase second harmonic. And if I twist the pot back to that original position, you see I can get this figure 8, and that's indicating that we're kind of right in between positive and negative phase second harmonic. So this is actually this is pretty useful to know. And oftentimes when we talk about feedback and things like that, we talk about feedback in abstract terms. We talk about the block diagrams and so forth, which is certainly perfectly legitimate way to discuss feedback. But it's also good to know what's really happening and how it's affecting the characteristic curves of the device that you're applying the feedback around. Okay, so I promised some weird amps, so here we go. Starting with Glow-fett. First of all, I'd just like to say that building the weird stuff is one of the great benefits of DIY audio, you get to build things that you could probably never buy, and experiment with different techniques and different things. And so for me, that's part of the fun. And Glow-fett came from, I took a long break from audio, and Glow-fett came from a desire to come up with a kit or a design that would be easy for a beginner that included a vacuum tube. And when I was young, I grew up on reading Sound Practices and Vacuum Tube Valley, and I used to look at the schematics in those things, and for some of the single-ended triode stuff, like J.C. Morrison stuff and Herb Reichert stuff, and I look at those schematics and I think, well, that looks really simple. I could probably build that. And then I looked a little closer, and some of the iron for that stuff was really expensive back then, and the tubes were expensive. And then moreover, I looked closer, and what's that power supply? 450 volts, and I wasn't ready to build 450 volt power supply just yet. And then I recall it wasn't long after that Nelson published the Zen project, and I thought, here we go. I can handle this. The voltage is pretty low, and it looks really simple. And so that's where things really kicked off, and I got started. So I thought it would be great to come up with something that a beginner could build that didn't have dangerous voltages and had a vacuum tube in it. And I didn't just want to include a vacuum tube. The vacuum tube had to have a reason for being there, and because I wanted, I wanted to give somebody a taste of that, that flea-watt single-ended triode sound with something that they could maybe build over the course of a weekend and plug in and listen to and have fun. So that gave rise to the original Glow-fett, and that's this one. That's their mono blocks, and this is one channel, and these are there's an identical pair of these at Nelson's place. These are the ones that went to Sea Ranch, and the concept behind these is we talked earlier about voltage feedback and how it changes the drain characteristics of the FET, and instead of a resistor divider, we can insert something else into that circuit. We can put a vacuum tube in there. Potentially we could put in an SIT or a JFET or something else, but in this case we're using a vacuum tube, and the voltage from the drain feeds right back into the plate circuit of the vacuum tube, and so the vacuum tube is going to impart some of its flavor onto the MOSFET, and it's going to change those characteristic curves to look more tubey, not surprisingly. This was the original, and I started out by collecting a lot of tubes. I've got a closet full of tubes now, and what I did was I used Locky Z's curve tracer, and I just made a little heater supply, and I measured a whole bunch of tubes at low voltages to find something that I thought looked interesting, and I tried I tried the little tubes, that were used for automotive and stuff like that, and those are getting pretty rare and expensive, and also they didn't really have the kind of curves that I was looking for. And finally, I hit upon this 6N6P, which is a Russian tube, and it's a pretty sturdy, attractive little tube, and it has the benefit of the grid current. It doesn't really start to surge until about plus a half a volt, and that's important because we're using these things so close to 0 volts that we don't want too much grid current to flow, or we could heat up the grid and upset our bias arrangement and things like that. I should also point out that this usage of the triode in the feedback circuit, I've seen that done by others. Shamichi Kamijo, I hope I'm saying that correctly, did this with pentodes, and John from TubeCAD has done this with tubes and MOSFETs, albeit at higher voltages and often transformer coupled. We're trying to come up with something considerably simpler here, and this is what it looks like. It's choke loaded. Got a 60 millihenry inductor there, L2, and just a 19 volt switching power supply. The MOSFET here is a lateral part, and that's one of those profusion parts, and that's the big one because we're going to dissipate some wattage here. I've got a 0.1 ohm source resistor in there, and it's really just there for convenience to measure the bias current. And we've got on the cathode of the 6N6P, got a 500 ohm or a 499 ohm cathode resistor, and a 10K potentiometer that allows us to set the bias on M1. And then over in the input circuit, we've got a 60 Henry inductor in parallel with a 22K resistor, and that's we could potentially just use the 22K resistor, but again, I mentioned that grid current surge, which is going to drop a little voltage across whatever we put there. And the L1 has a much lower DCR, maybe I think 3 or 4K, and this has the benefit of if we when we get to higher power, the grid current doesn't drop enough voltage to really upset the bias too much, and we want to avoid doing that situation all the time because it can heat up the grid and upset our bias arrangement. So there it is. Here's what it looks like performance-wise. So bias currents ranging from 1.6 amps here to 2.5 amps, and you can see if we put a lot of current through there, we can get semi-respectable performance out of this. That's what, 2, 3, 4, 5.04 THD at a watt. But again, we're trying to mimic a little flea watt single-ended amplifier here, and so at 1.6 amps, I called it totally tubular because that was sort of its tubiest, most operating point for me, and I sent those to Sea Ranch, and I think Nelson agreed. I think he had fun with them. Here's the distortion residual, and That's a negative phase second harmonic on the screen there, but it's an inverting amplifier. So if you preserve absolute polarity, you're going to flip those speaker terminals, and you're going to end up with a positive. Here's the THD versus frequency, and we've got that inductor load in there, and that's given us the that rise at low frequency. Here's our frequency response, and we're down about -6 dB at 200K, but pretty flat, not bad looking. And here's a 10 kilohertz square wave, nice and clean. Some other specs, the noise was 280 microvolts unweighted and 19 microvolts A-weighted, so that kind of tells you where the noise is, and so this one might benefit from that filter. The output impedance is a nice 2B 8.5 ohms, and the input impedance is around 20K ohms, and the gain is 15 dB. And that brings me to the Gutenberg variant, which is, this came from, Nelson did a YouTube interview with Steve Gutenberg, and he mentioned these amps. And Steve said something. He said, change the tube, change the sound. And I got to thinking, I was like, well, Steve, he probably likes to roll tubes, but he's not going to want to mess around with, having to readjust that bias every time he changes a tube. So I came up with this. This is a couple of things here. Remember, I mentioned that it's an inverting amp, and we end up with a positive phase second harmonic, and so. Nelson said, well, hey, why don't you put a transformer in there? And so I've done that. I put a transformer in here. And then in addition to that, we've got this sort of auto bias circuit in R4 and Q1 there, R3 and C1. And you'll recognize this as kind of a current limiter. We've seen this circuit before in current sources and so forth. And that is, you can see Q1 is attached to the bottom of that transformer, which is then attached to the grid. And that has the effect of keeping the grid at a place where the bias current will remain at about 1.55 amps. When we're dropping about 0.6 volts across R4 there. Additionally, I tossed in a cathode resistor and a pot, a 1K pot, and the greedy boys would call that a Zen pot. So the bias remains at 1.55 amps, but we can change that cathode resistance a little bit and kind of tweak the load line a little and change the harmonic character of this thing. And so not only can you plug in different tubes without resetting the bias, but you've got a knob where you can tune the harmonic character a little bit, kind of like a sit one. And to illustrate that, here's the THD versus level, and each of those lines represents a different setting on that 1K pot, and you can see that that we can dial the distortion down to a very low level if we want, but that comes at the expense of a lot of cancellation and a good bit of third harmonic. And if you're trying to maybe mimic a single-ended, 300B or something like that, maybe that's not what you want. Maybe you want something like the aqua line or the purple line there. So you've got a good bit of adjustment you can do here. And here you can see those characteristics. The first couple of pot positions, nice clean second harmonics there, and even position 3 is still a nice clean second. 4, starting to get a little third poking up through there. And 5 and 6, right, we're really starting to see that third harmonic poke up through there. And you know, the number's lower, but maybe it's not the characteristic that you want. Here's the THD versus frequency, and a little bit of a smiley face effect there. Again, this is primarily due to the choke loading. The transformer might be contributing to that. I should point out that transformer is just like an $8 jobby from Triad. Nothing fancy. In fact, I tried fancy stuff, and I wasn't able to get a good clean square wave with those things without, you know, a lot of gyrations and loading and so forth. And I wanted to try to avoid that, and I was able to with this cheapy Triad input transformer. And here's a 20 kilohertz square wave, and it's pretty clean. There's the frequency response. I mean, we're barely down at 200K, so lots of bandwidth. Again, 280 microvolts unweighted, 19 microvolts A-weighted, and again, maybe put a filter on that, and that would be even better. The output impedance in this case is 2.5 ohms. And the input impedance is a little over 20 k ohms, and the gain is 15 dB. I want to go back to the schematic for a second here, and just note that this is now just a garden variety IRFP 240, so we didn't need to use the lateral in this case. And the power supply, I should also mention, is no longer 19 volts. It's 24 volts on this one. And I needed that extra voltage because we need some more voltage to buy us up the IRFP 240. So not only can we use the 6N6P and different 6N6Ps, you know, each one's going to sound a little bit different. But you can try other tubes as well. Your mileage may vary, but you know, if you're in this for the fun, then here are some other tubes. There's a 6GM8. I've got a 6N30Pi, which is like a big brother to the 6N6P. It's a little more expensive. Here's a 6N7, one of those fancy tennis ball triodes. You know, there's a whole bunch of those available now. There's a 6922, 6DJ8, and all of these are pretty good dominant second harmonic. There's an E88CC, an ECC86, and there's an ECC99, and the THD is, again, you know, pretty low, but we got some cancellation and we got some third harmonic poking up through there. And just for fun, I tossed in a 12 volt tube, the 12BH7, and look how low that is, but it's also dominant third harmonic. The heater supply for this, by the way, I didn't show it in the schematic, but it's just nothing fancy. It's just an IC regulator giving us 6.2 volts for the tube, and it's just derived from the same switching power supply with a couple of dropping resistors to keep the dissipation down on the regulator. The the final schematics and parts lists and for all of these projects I'm showing you today will show up online, and when they're complete. So we're just kind of previewing this stuff today. Yeah, watch for the kit at DIY Audio. So eventually this will make its way into the world as a kit, and I just need to work out what the form factor is going to be. I want to get some input from Nelson and Jason. We could do this in a 4U chassis or a slim 4U chassis, or we could even do it in the. I'm kind of partial to that big circuit board that just kind of sits on top of the wood box, because it looks like a tube amp. But we'll see where we end up there. So that is the Glow-fett. Okay, one more weird amp here. This is ultralight, and that's what it looks like. This came about because I got a pair. You can see them in the background. I got a pair of these speakers from Lewis at Omega Loudspeakers, and it's a full range, like 4.5-inch driver, and a bass reflex tower, and I believe they're called the Super 3 SRX or something like that. Sorry, Lewis. But at any rate, I got those speakers, and I really liked them. They're surprisingly smooth. The driver is. It looks like a Fostex. I think it's something that Lewis has made up special. But at any rate, they're surprisingly smooth. They don't really sound like a Fostex, and their only limitation is, you can't play them really loud or they start to do the Fostex thing. But I thought they sounded really great, and I thought they sounded especially great with, I've got a 300B amp that I put together, and they sound nice with a good bit of second harmonic and a high output impedance, and so I put something together just for those. And as you can see, I kind of threw the kitchen sink at this one. It's got we got this nice 500-watt light bulb in here, it's like 10 inches tall. It's massive, and got a big choke that's like a 200 millihenry choke, and got a 6SN7 and a lateral MOSFET. Here's what it looks like. So I was shopping for switching power supplies, and I found a cheapy 48-volt power supply from Jameco, and I thought, well, yeah, 48 volts, that'll give me a little higher voltage on the tube, and kind of get us away from 0 volts on the grid and so forth, and get us little more into the linear region of operation. And of course that presented a problem. I can't run the MOSFET at 48 volts or with any significant current, or we're going to have a dissipation problem. So we've got this 500-watt lamp in here that has a resistance of about 12 or 13 ohms, and so that's kind of acting as a level shifter. So the tube is close to 48 volts, and the MOSFET is running down at 24 volts. And so not much to it. We've just got an adjustable resistance in the cathode here, and a 50k ohm resistor on the input to pull that down. And I'm using kind of a high gate resistance there in R3, and that's just kind of helping me tailor the output the way I want it. We'll take a look at the effect of that here in a second. But I called this kitchen sink amplifier ultralight because there is kind of an interesting feedback situation happening here, which is that the feedback is somewhat frequency dependent, because I've got this inductor that has a very high impedance at high frequency. So at higher frequencies, the plate is very close to the drain of the MOSFET, because the impedance of this is so much higher than the impedance of the lamp. At lower frequencies, these become more equal, and so I get a different feedback division. But the effect is, it's not really quite like ultralinear. I guess it would be maybe frequency dependent ultralinear, and it's pretty subtle because I've got a big 200 millihenry choke in here. So I also, in addition to that, I put in some jumpers, and so that I could put some a feedback loop on it if I wanted to, and I did that so that I could get a lower output resistance, so just so that I could listen to different output resistances. This is what it looks like with 2 amps bias, and the red line is without feedback. The blue line is with feedback, and it's not too bad, and it's certainly as good as my 300B amp and a lot of other flea watt amps that I have around. And here it is at 1.6 amps, and of course the distortion is higher, but I think it sounds even tubier there. So again, the red line is without feedback, and then the blue line is with adding a touch of feedback in. Here's the THD versus frequency, and a little bit of a smiley face, but not too bad in this case. So, and here's the distortion waveform. Oh, let me see. No, I missed a slide for you. The frequency response. Here's the 1 watt distortion waveform, and that's a nice clean negative phase second harmonic. This amp inverts, and so if you want to observe absolute polarity, you're going to flip your speaker terminals. So you would need to go back. You could put a transformer on the front of this and flip the phase that way. Or you could, if you have, like me, if you have a DAC with a phase invert switch, you could just use that. Perhaps we could get Nelson to design us a nice phase inverting buffer circuit at some point that we can just, that would be handy. Oh, there we go. There's the level versus frequency. And you can see we're minus 4 dB at 200 kilohertz, so it's good bandwidth. And here's the 20 kilohertz square wave. Nice and clean. Nice John Atkinson approved 20 kilohertz square wave there. Other specs, noise, not much noise at all. 23 volts microvolts unweighted and 15 microvolts A-weighted. The output impedance with no feedback is 12 ohms, and with feedback it's 8 ohms. And the input impedance is about 50K, and the gain is about 15 dB and 10 dB with feedback. So here's what they look like. And if the last amp was for Steve Guttenberg, these are for Herb Reichert, because these have the halo, and I think if Stereophile had a category for best glow factor, I think these would be a contender. So these are a lot of fun. These probably won't. I don't imagine these will show up as a kit. They're really simple, and you could just wire these together point to point on a piece of plywood, as I've done here. Okay, one last big announcement before I go. Past DIY is coming to YouTube. And the idea is to create a great place for us to hang out and post projects, tutorials, how-tos, Q&As, interviews, demos, audio, lore, and more. So join us there. And we need your help today to help us kick this thing off. We need to get to 100 subscribers. So please go to pastdiy.tv and click subscribe. Or as the hipster influencers would say, like and subscribe. I'd like to thank everybody. It's time to say goodbye, but thank you very much for inviting me to give a presentation this year. And I'd like to thank our other presenters, Stephen, Damien, Andrew, and Nelson. Thank you very much. And I'd especially like to thank our organizers, Tom and Mark, and perhaps a host of other names that I'm not familiar with. Thank you all very much for doing this, because I know it's a lot of work. And I wish that we could have been together, but I'm glad that we did this online nevertheless, because I didn't want to skip another year. So hopefully I'll see you next year in California. Thank you very much.